By themselves, the elementary functions are not particularly powerful or useful, although sometimes they might be. But with each of these elementary functions, we can manipulate them. We can change their form by, let's say, multiplying the value of the function by some number, or by adding or subtracting some number to the value of x before evaluating the function. So, in general, let's just start with the linear function and see how that might work. Okay, your linear function, f of x equals x. If we have the x-axis here, the y-axis here, the f of x function makes a 45 degree with the x-axis and passes through the origin. Now, there are a lot of infinite number of straight lines that we can draw in the plane. Some of them are higher, some lower than this basic function, some steeper, some less steep. We can manipulate the steepness of a linear function if we multiply x by some number. So if we multiply x by number a, then the graph gets steeper if a is greater than 1, less steep if x is less than 1, and of course the slope can go negative by using a negative number a. So we get it more steep and negative, less steep and negative than the basic f of x function. By adding a number after multiplying by whatever number we use to get the slope that we want, okay, we can raise or lower the graph. So if we want a graph of a function up here that has a slope like this, we can start with our basic f of x function that passes through the origin. We can multiply it by a number, say about 1/3, which gives us about 1/3 the slope, and then we can raise it whatever this distance is, and now we have the graph that we were looking for. So by choosing the right number a and b, we can transform this function into this function. The transformation that we get when we multiply x, or when we multiply the value of the function by a number, is called a vertical stretch. Okay, if we want to make the graph steeper, we multiply it by a number. Let's say we want to multiply by number 2. Then the graph is going to get twice as steep. It's going to have twice the slope. Okay, steepness is not necessarily the same thing as slope. Depends on how you want to measure steepness. It's not a mathematically precise term. Okay, so we multiply by some number a, and we can make the graph steeper, or we can make it less steep. Of course, we can make the slope negative. So really what we're doing when we multiply by a is we're changing the slope of the graph. Then when we add a number b, we are raising or lowering a graph. So when we multiply the value of the function by a number, we do what we call a vertical stretch. If we imagine that the coordinate plane is like a piece of taffy, if you've ever seen taffy, I guess it's 3D printed by now, but you stretch everything like this, and this graph would get steeper. Or if you do a stretch by a number less than 1, well, that's like compressing the graph, and the basic f of x graph would get less steep. And of course, then we have what we call a vertical shift. We shift the graph up or down by adding a number to whatever we get after we do the vertical stretch. Now, we developed that in a little more detail. I've gone a little deeper. I've said a little more about it than I really had intended, but we want to get an idea that these parameters have a geometric interpretation. So these parameters, and I just used the word but without defining it, the parameters of this function are a and b, where a dictates the slope, a is the slope, and b, turns out, is the y-intercept of your linear function. So we can get any linear function using a vertical stretch by factor a and a vertical shift b. Now, without going into all the detail about what these stretches and shifts do, if we have the power function f of x equals x to the p, we can generalize this function. Now, up here, the most general linear functions, f of x equals ax plus b. Any linear function can be expressed this way. Any function whose graph in the Cartesian plane is a straight line will have some value of a, some value of b, and will satisfy this equation, or will be modeled by this equation. Two parameters, a and b. Okay, for a power function, for general power function, without going into a lot of explanation, we have a vertical stretch by factor A. We have a horizontal shift. Okay, so we take this power function, which might have a graph that looks something like this or like this. Okay, we can stretch it to make it steeper or less steep. We can shift it to the right or left. If we add h, if we subtract h from the value of x before raising it to a power, that has the effect of shifting the graph h units to the right, as you might know by having memorized the rule, as you might even understand. We develop an understanding of why that happens. And then if you add k, it's not hard to understand that if you add k to whatever you get here, that's going to make f of x k units higher. But it's going to change the vertical position of the graph by k units. If k is positive, the graph is just going to go as a piece higher. If you have a negative k, that's going to make the graph go lower. Okay, there are three parameters here: the big A, the vertical stretch, the horizontal shift, and the vertical shift, k. Okay, those are three things that you can do. And if you have any generalized power function, any function of this nature, you can get it by manipulating those three parameters. Now you have quadratic functions. When you generalize a quadratic function, you use the same three parameters that you would for a power function. Okay, and also there's another form that's more familiar. This is f of x equals ax squared plus bx plus c. This is something we'll call the vertex form. The graph of a quadratic function is a parabola. The coordinates of the vertex of the parabola are hk. And then the steepness of the parabola, the narrowness, is affected by the value of a. If we square this, multiply everything out, we can put this in the form ax squared plus bx plus c, where little b, and little c are directly related to big A, little h, and little k. We don't generalize the polynomial function. At least we're not going to do that at this point. We could add parameters to generalize it, but we're not going to. By the time we get into analyzing polynomials, we'll understand how these transformations work. With an exponential function, we can generalize the exponential function using parameters a, b, and c, where b is regarded as a parameter, and we can create any exponential function in this form, or we can generalize it using this special number e as a e to the kx plus c, where k now is not a vertical shift, but it's a different kind of a number. These two forms are identical in effect, but the numbers are different. The a number for both of these would be the same. The c number would be the same, but the parameter b and the parameter k would be related by b equals e to the k, or alternatively by k equals a natural log of b. Now, if you don't know about natural logs and exponential functions, you won't understand what I just said. But let's move on to the idea of a logarithmic function. The logarithmic functions are inverse to the exponential functions. So your basic logarithmic functions are going to be the base b log to the base b of x, and the natural log, ln of x, natural log of x. These functions come directly from these functions by the inverse function relationship. Again, something you might or might not be familiar with it in some sense, but it's a fairly easy idea once you've worked through it in a little bit of detail. And it just simply says that the log to the base b of b to the x equals x. Okay? Or the natural log of e to the x equals x. These two relationships, this relationship defines log to the base b. This relationship defines the natural log. And once you have this definition, this whole idea that these are the same under these conditions falls into your hands very easily. But it takes a while to get used to the exponential and logarithmic functions. You have to get really good with the laws of exponents to understand these things. once you're really good with the laws of exponents, it's not that bad, and it's kind of neat. It's like the log function cancels out the exponential function. So if you had an equation involving exponential functions, if you take the log of both sides of those equations, after you get it into the right form, it kind of cancels out the exponential, allows you to solve the equation. Okay, we have to talk about that in much more detail. So again, we have three parameters that control the exponential function. I don't write down the generalization of the logarithmic function, although that can be important too. You get the idea that you have usually three parameters, sometimes four, as we'll see in a minute, that govern how we go from the basic elementary definition of the function to the generalized function. And the generalized functions are extraordinarily useful. Okay, for the trigonometric functions, let's just take the sine function, because that's one I've written out most clearly. The generalized function is f of x equals a times the sine of the quantity b times the quantity x minus h plus k. This is a four-parameter function. A widens or narrows the sine function. Of course, you probably understand a sine function has this wavy appearance. So you make it wider, you make it higher, you make it lower. You increase its amplitude or decrease it. That's what A does. And A is actually what we call the amplitude of the sine function. It tells you maybe how powerful the function is, if that's what's going on. Okay, the B takes that sine wave and can either spread it out or compress it like an accordion. So a large number B will compress the equation like an accordion. A small number B will spread it out. Will stretch or spread out. I'm sorry, compress or spread the graph in the horizontal direction. H is a horizontal shift that accomplishes what we call a phase change. Again, we'll have to talk about that in detail. And K just raises or lowers the graph. So we have these four parameters, and with these four parameters, we can create any sine wave, any sine function. You can do the same with the cosine. I haven't written out, well, I've written out the general form, and you can do the same with the tangent. Then you have the inverse trigonometric functions, which we don't typically generalize. And as we will see, we do generalize the absolute value function with three parameters, a, h, and k, that have the same effect as the a, h, and k for any of these other functions. Now, by generalizing these functions and then combining these functions by adding functions, say add an exponential function to a power function, or multiplying, a lot of things behave according to a product of an exponential and a trigonometric function, a sine or cosine usually. Okay, so we can combine these functions. We can do composites of these functions. We can do an exponential function of a power function. For example, e to the x squared. X squared would be a power function for p equals 2. So if we did e to the x squared, we would have what we call a composite of the of the natural exponential function, if you wish, with the squared function. And if we do that with a negative x squared, we get the famous normal curve, the bell-shaped curve. So there are all kinds of applications that we can get by combining these functions. And when we do all the possible combinations of elementary functions, we really have pretty much the whole picture of all the functions that we use in the in a first-year calculus course and in a second-year calculus sequence, up to the point late in a differential equations course where you get special functions that are defined by differential equations, and those are no longer elementary functions. But we can do almost everything that we do in some very powerful mathematics with just elementary functions, and it's an important classification to understand.